Alright guys, welcome back to Machine Organization. This is lecture 9 and we've got some awesome stuff planned for today. We're going to be looking at low-level C programming and we're going to start off with a little review and then dive right into number representations. Alright guys, today I'd just like to start off with two practice exercises to get us started. This is mostly review, but here's what we're looking at. So this is the first question. Basically, assume that we've got a function here, string copy, and its goal is to make a copy of this string s. So this function actually has a bug in it. And what I'd like you guys to do in a second is pause the video and just take about 4 minutes and read this and see if you can find the bug. I'll put up the man page in the video for string length. You can pause the video and read that. I'll put up the man page for string copy. You can pause the video and read that. If you're working at home, I recommend you pull these up yourself and just do it on your own computer. Good practice. And then I'd like you guys to just assume that everything here in main works perfectly. We're going to declare a string and pass it to this function, get something back, and then maybe print it out. I'm going to leave this as an exercise for you guys to write. And on exam questions coming up, I will post links to man pages for things like string length and string copy for questions of this nature, just so you guys are aware that you'll have that. All right, so let me pull those up. I'm on the wrong screen. And string length. All right, there you go. Pause the video here and read this. And then let me pull up string copy. Copy. Pause the video here. Go ahead and take a look at this. And then I'll pull the code back up. And pause the video here. Take about 4 minutes now and just see if you can spot the bug. And I'll be right back with the solution. Alright, so what we have going on here, or welcome back. If you didn't pause the video, do it now. Try again. What we have going on here, the real problem is with this string length function. So let me just make a note here. If I have a string, character array, s is equal to CS354. All right, what this is going to do, this is going to reserve space for all 5 characters, CS354, and an extra one for that \0. So in memory, we'll have C, and then S, 3, 5, 4, and then \0 to finish it up. And I meant that one. Okay, so this is what we've got. So 1, 2, 3, 4, 5, 6 characters in memory. The problem is that string length, strlen, only counts the non \0 characters. So this will be 1, 2, 3, 4, 5. It'll return 5 characters. And the other issue that might be a problem for things that are not strings are going to be the fact that the number of bytes, this reserves bytes. And we may... All right. Stop that. Mute your phone mic. Sorry about that, guys. Okay. This is going to reserve the number of bytes. Now, characters are 1 byte each, so it's not a problem for characters. But if we have an array of other things, or if they change the length of a character, or if you're programming in C++ and you're using wide characters, this will be an issue. So what this line really should read is something more along the lines of malloc. And then what we want is strlen of s plus 1, and then we'll multiply by size of char. And I didn't do the char d. This is the second half of that statement, the right-hand side. All right, the rest of these things work just fine. So if d is equal to null, and remember, if you run out of memory or there's some sort of problem with malloc, it will return a null pointer. So it's always good to test this. And if there's no copy, return null, and then that can be tested for in main just to verify that this function worked. And then string copy or str copy works just fine. There's a better version, str n copy, where it takes one more parameter, and that's the destination, the source, and then the number of characters to copy. Highly recommend using that one instead of str copy. That way, if there's a problem like this, you're not going to overwrite extra memory, and just sort of keeps things straight. If there's a problem with your original string, if there's no \0, it's just going to copy tons and tons and tons of characters until it happens to run into a 0 by accident. And then return deep, this is a pointer, we're returning a char start, we're returning a pointer. So all of this is fine. All right, go ahead, just as an exercise on your own, fill out the rest of main and test this, and just make sure I didn't screw up. Let me know if I did in Piazza, and then I'll get it fixed and put like a little note there. All right, let's see, quit. I'm going to take out those comments so that these are not available when you guys do this the first time through. If you're interested, you can type that yourself. All right, so we'll not save that. Next up, second practice problem. All right, guys, I've got a second practice problem here. Take a look at this one. The question is, what is this going to print out? So in a second, go ahead and pause the video and take about 4 minutes and just make your best guess. Write it down, commit to your answer, and then see if you're right. All right, and I'm going to go ahead and I'll tell you a little bit more about how this line right here, this hash defined array length A, if you happen to have skipped that chapter in the book, I'll go ahead and explain it. But if you want to take your best guess here, go ahead and pause now, and then I'll come. If you run into trouble understanding this line, come back. I'll explain that first, and I'll give you another chance to pause. Okay, so the way this hash define works, it's going to take this variable right here, array length A. This is going to be a compiler variable, not a C variable. All right, so during the processor stage, all this does is it's going to take all of these defines and just copy and paste whatever this is directly in there. So it's used twice. I've got my array length compiler variable right here, and it's going to copy this text right there. Now the parentheses here means that this particular compiler variable does take a parameter, A, and so the parameter here, P, gets replaced anywhere there's an A up here. So this array length P section right here will be replaced with size of P divided by size of P bracket 0 bracket. All right, so go ahead, pause the video, make a prediction, commit to it, take about 4 minutes and give this some serious thought. And then come on back and I'll tell you the answer. All right, so we really have two pieces here. This top part where we're using a pointer and we've reserved some space on the heap with malloc. This is going to be array. It does have enough room for 5 integers. And then this array length right here is going to be size of P divided by size of the first element of P. So the compiler knows that this is a pointer to an integer. So this, here, let me make some little notes here. We're going to have the heap, whoops, and on the heap we're going to reserve space for P. This is going to be, I'm just going to, let's pretend they're filled in with zeros. 2, 3, 4, 5. There we've got space for 5 elements in this array. Pretend they're filled in with zeros. Initially, nothing is pre-allocated. It's not going to be predefined to 0. That's not the right word. I can't remember it. Okay, my mind is blanking. Anyway, so let's pretend for a second so we can predict what this prints out. So the next thing it does on the stack, we're going to have a pointer to P, and this is going to have the address of this array in on the heap. So when we go through this and use this size of P, what it's really doing here is going to be, I'll just put right next to this. So this will just be a comment on my stack. Size of, and this is, it knows it's a pointer, so it's going to be size of a pointer to an integer. Okay, and that's going to be 4 bytes on a 32-bit machine. The next thing it's going to do is divide that by size of the first element. So that's going to be size of, and it knows that this is a pointer to an array of integers from right there. So this will be a size of int, which let's assume that it's also 4 bytes here. And so this will do 4 divided by 4 equals 1. So when I go through this list, I starts at 0, I less than 1. It's only going to go through the loop one time, and it'll print out whatever happens to be in P of 0 in this case. All right, so the next half of this is I'm declaring array A. This array is going to be on the stack. So I'll have my variable A, and this is going to have, let me do it this way. Let's see, 1, 2, 3, 4, and 5. It'll have 5 numbers in it, 1 through 5. Now, let's take a look at this loop. When I'm using this macro replacement to get the array length, remember this is a compiler variable, and the compiler knows that this is an array that has exactly 5 elements in it. So this size of use with arrays works differently for things declared on the heap and declared on the stack. So let's see here. Let me move this down. And then real quick, this will be the equivalent of size of, and this is not int 5. This is int, whoops, not a pointer. This is int 5. So it knows that this takes up 20 bytes. The size of int, let's see here. Yep, size of int 5. I need a parenthesis. And then we'll also have size of int because it knows that it's an array of, so this first element is an integer, so size of int. Got an extra one of those. So this is going to equal 20 divided by 4, or 5. Okay, I'm just going to go ahead and, let's see, I'm not going to, yeah, we'll go ahead. No, I'm not going to save it, so that when you guys actually get to the code and try this for yourself, you don't have the answer right here. So I'm just going to force quit. So if you need to, take a screenshot or pause the video, memorize what's there. And now if I compile this, gcc-o, I'm just going to call it Q2. The original code is review q2.c 32 to get the right number of bytes on all warnings. And it does give us a warning. It's just reminding me that size of int pointer divided by size of int does not compute the number of array elements for things declared on the heap. And that is going to be called for P only. All right, and from here. So this is where I declared P. This array length P gives me the warning because this array is on the heap. It doesn't give me any warning at all about the lowercase a array. That one works just fine. And let me think, I call this Q2. We'll run this, and indeed, it only prints out the very first element in P. It only goes through that loop one time because it's doing that size of pointer, which is 4, divided by size of int, which is 4, and gets one time through the loop. For the other array, we do print out all 5 numbers because it knows that the array length or size of an array of 5 elements takes up 20 bytes, divided by the size, 4 bytes. So this one works as we would expect, and we get A0 is 1 all the way through 5. All right, so let me know if you have any questions about how this works. Try it yourself. Put those questions on Piazza, and we'll take a look at them. All right, I'm recording these segments a little bit out of order, but hopefully I just wrapped up with a little bit of review. And now diving into number representations. We've talked mainly about using just sort of the unsigned binary representation for numbers up to this point. And if we well, let's see. Let's just assume that we're going to be using 8-bit numbers. And in fact, some of my demos in just a second, I'm going to drop down to 3 so I can write out all the possible different numbers that we can represent. But for this first example, what is the maximum integer that we could actually represent using 8 bits? All right, the easy way to think about this is to just put a 1 in every single bit position. So 1, 1, 1, 1, 1, 1, 1, 1. So all 8 of them are 1s. If we did all zeros, then we would say that that's would represent the number 0. But so for this method, what we've been doing for unsigned number representations is just saying that this rightmost one is going to be 2 raised to the 0 power times this bit, and then 2 raised to the 1 power raised to times the value here, and then there we go. Then 2 raised to the 2 power, then 2 raised to the 3 power. And so if they're all 1s, these all get multiplied by 1. I didn't show that. And then when we multiply that out, 128 plus 64, dot, 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 plus 1, we find out that the biggest number we can represent using 8 bits is 255. But that leaves a question for us. What if we wanted to represent negative numbers? So I'm going to switch to 3-bit examples so I can draw out all the possibilities here. The way I was just doing it with the unsigned version, I would get the numbers 0 through 7. Now, we know that C lets us use negative numbers. Very important for a lot of things. So how could we do that? So one solution is to just use one of those bits as a signed bit. So here's my old version. If I were to just say that the most significant bit here, the one on the left, will just represent the sign instead. And then we can say that 0 is going to be a positive sign and that 1 is going to be the negative sign. And we can just use the rest of the bits to represent the magnitude of the number. This is known as sign magnitude representation. So let me just walk through this. For the positive numbers, I've got 0 as the most significant bit, so that's going to turn into my plus sign right here. And then the rest of these, 0, 0 is still 1. 0. 0, 1 is still 1. 1, 0 is still 2, and 1, 1 will still be 3. So this is 1 times 2 to the 0 power plus 1 times 2 to the first power, where 2 plus 1 is 3. Okay, and then for the rest of these, the 1 here will represent the negative sign, and then 0, 0 is still going to be 0, 0, 1 is still 1, so 0, minus 1, minus 2, minus 3, and 0, 1, 2, 3. So it just repeats itself. There's one significant downside to using this signed magnitude representation, and that's we have 2 different ways that we can represent 0. There's a positive 0 here at 0, 0, 0, and there's a negative 0 at 1, 0, 0. And so this leads to all kinds of problems. It's really difficult to do in hardware. And if you think about it, what do these things mean then with these 2 different binary representations? Are they exactly equal? Is the negative 0 less than the positive 0? Less than or equal to? So there's some challenges with using this sign magnitude representation. In fact, early computers did use this as the way that they represented negative integers, but I don't believe they're used in any modern machines at this point. All right, so next up, I want to talk about a second number representation. I've got 3 total for today. So this is another way that we could use to represent negative numbers. It was used in a number of machines, but I don't believe it appears in very many modern computers. And this is the ones complement method. So complement just means that we're going to flip all of the bits and use that for the representation of negative numbers. So by flipping the bits, what I mean is here 0, 0, 0 would represent, positive 0. But then when we flip all the bits, so 0 becomes 1 and 1 becomes 0, we end up with 1, 1, 1. Well, let's take a look at this one. 0 here becomes 1, the second 0 becomes 1, and the 1 flips to 0. So that's all I mean for that. So then we know we're going to use these numbers to represent the negative numbers. So the 1 still gives us a clue that these are the negative numbers. They all begin with 1. But we just translate this 0 here directly across. The 1, when we take the complement, becomes minus 1. The 2, when we take the complement, becomes minus 2. And if I were to rearrange this and draw the full list like I had before, see I get 0, 1, 2, 3, just like before for all the positive numbers. But then we get 3, minus 3, minus 2, minus 1, and minus 0. And this has the exact same downside in that now I've got 2 different ways to represent 0. So 0, 0, 0, and 1, 1, 1. So, yeah, this is a bit of a challenge. It was used, but we now have a better method that's used by almost all modern computers. I want to teach you guys one other algorithm for calculating the ones complement. Basically, we're going to subtract whatever the positive representation is for a number from the bit pattern that has all ones. So, for example, if I'm going to figure out what is negative 1, I'm going to take the bit pattern for just regular 1, which is 0, 0, 1, and I'm going to subtract that from the all ones pattern, 1, 1, 1. So here, look, starting from the right, 1 take away 1 is 0, 1 take away 0 is 1, 1 take away 0 is 1. And if we flip back a slide, we can see that negative 1 is indeed 1, 1, 0. 1, 1, 0. Okay, another example. If I'm looking at minus 3, when I have 3 as a positive number, I've got 0, 1, 1. So 1 plus 2 raised to the first power times 1, or 2. 2 plus 1 is 3. Okay, and I'm going to just subtract that from 1, 1, 1. Okay, when I do that, if I look at the rightmost one, I've got 1 take away 1 is 0, 1 take away 1 is 0, and 1 take away 0 is 1. And so that's going to give me 1, 0, 0 as the bit pattern representation for -3. If I flip back a slide and find -3, I see that it is 1, 0, 0. All right, and finally, the third representation that I'm going to introduce today to talk about number systems is the 2's complement method. This one is currently used in modern computers all over the place. And also notice that the most significant bit is still going to represent the sign when we're done with this. This is true for all 3 number representations. You can see whether a number is positive or negative by just looking at that leftmost bit. Okay, but we're going to make one simple change to that formula that we had been using, like the very first one when we had the unsigned binary. We were converting those to just decimal numbers. We're just going to make one change, and that's this negative sign right over here on the leftmost number. So the leftmost bit, the most significant bit, is going to be, instead of whatever that bit is, B2 is a 0 over 1, times 2 raised to the however many bits there are. For my example, I've got, 3 bits, so this is 0, 1, and 2. And I'm just going to add a negative sign right there. So maybe an example would make this a little more clear. So let's take a look at what this formula does as we plug in some numbers. So in the case of like 1, 0, 0, I'm going to have -1 for that. B2 is a 1. The negative sign came from right there, and then 2 raised to the second power. And then I have a 0 here, so B1 is going to be 0 times 2 raised to the first power. 0 times anything is 0. And then 0 for the third bit times 2 raised to the 0. And again, 0 times anything is 0. So I end up with -4. So there's the minus. 2 squared is 4, plus 0 plus 0. So this was going to represent -4. Just one more quick example. For 1, 0, 1, I still have B2, the leftmost bit is 1. So -1 times 2 squared. And then I get a 0 times 2 to the first power. And then there's a 1 here, so plus 1 times 2 to the 0. So this translates to -4 plus 0 plus 1. And when I add those together, I get -3. And I'll leave the rest of these for you guys to do as an exercise, but 4, 3, 2, -1. Check this out. So at this point, the advantage to this system is we no longer have 2 different zeros. 0 is the most commonly used number in computer science, in C at least. It's used for false, it's used for initializing a lot of things, and we no longer have that problem of trying to decide if one 0 is equal to another one. There is only one kind of 0. All right, so next I want to take a look at, I just want to show that this still works for positive numbers. So all of these positive numbers over here in my number representation begin with a 0. So if I just look at one of them, the first thing I do is I'm going to take, all right, just made a quick correction to that slide. Hopefully you noticed that the minus sign is now there. Yeah, so I'm going to take the first bit here. There's a minus from the formula, so -0 times 2 squared. And anything times 0, even if it's negative, is still 0. So that's going to translate to a 0 right there. And then the rest of this bit pattern, 1, 0. So 1 times 2 to the first, 0 times 2 to the 0, is just going to give me 0 plus 2 plus 0, or 2, which is what I've been getting all along for that number, for that bit pattern. So I just want to show you guys another algorithm for computing the 2's complement of a positive number. So if I have n bits, I'm using 3 for this example, and I have a binary number 2 represented by 0, 1, 0. I can grab that right from the chart right there. The question is, how do we represent -2? So when I was doing this before, I had a bit pattern and I was going to the number. So this is sort of the opposite. If I know I have a -2, how do I get to the bit pattern? So the way we're going to do that is we're going to take 2 raised to whatever power. This is the number of bits I have, so 2 to the third in this case. And to represent 2 to the third, that's 8, I actually need 4 bits, so I'm going to have 1, 0, 0, 0. And then I will subtract the binary representation of, in this case 2. So 0, 1, 0, I'm going to subtract that. Now, if you're wondering how subtraction works in binary, where I've got 0 minus 0 is fine, 0 minus 1, how do I do that? Quick review of decimal subtraction, going back to 2nd grade. So if we have an example from decimal 151 subtract 85, we're just going to borrow from the decimal position to the left. So when I start out, I'm going to take 1 subtract 5. I can't do that, so I'm going to borrow from the 5 right here. So this problem translates into 1, 4, and then 11. So 11 take away 5 is going to give me 6. And then we'll do the same kind of borrowing again. I didn't draw it out, but so we'll borrow a 1 and we'll get 14. 14 take away 8 is going to be 6. So that's exactly how this is going to work. So let me pop back to this other slide. So I've got 1,000 take away 0, 1, 0. So 0 subtract to 0 is no problem. 0 subtract 0 gives me 0. And then when I borrow from this one position here, this will become basically a 2. And then we'll borrow again, and we'll get 1 and 2. So I realize I'm deviating from binary right here, but at the end I won't have any 2's. But you can think about it like this. So 2 take away 1 is going to be 1. As there, the 2 is gone. And then 1 take away 0 is still 1. Now when I look at this, 1, 1, 0, and I go over to my chart, 1, 1, 0, it matches up. I do get a -2. All right, I hope that makes sense. If you have any questions about this, put them up on Piazza. And I'm thinking, instead of making this kind of a long, boring demonstration where I'm just doing problems, I'm going to go ahead and prepare a worksheet and put that up with the answers onto our webpage to give you guys some practice. I think this will make so much more sense after you do just a couple of practice problems rather than watching me do them. This has got to be like the worst possible way to learn this stuff. So I'll put together a worksheet. You can go back and get some practice with each one of these sections. If you need to, you can like quick review the section of the video that's appropriate. When I release the video, I'll put a note in the email, just letting you know there's a worksheet that goes along with this. So you don't get to the end of this video where I finally decided to do that and have to go back and watch the video. All right, I'm going to pause for a second and then grab my next topic. Before I move on, I just thought I'd show you guys one other quick algorithm. This one might be a little bit easier to do in your head or remember than having to remember how borrowing works in binary. But so I'm calling this yet another algorithm. And this works, I'm going to do an example in 8 bits just to show you that it's, in my opinion, a little bit easier to think about. So if I take 3, the binary representation of 3 with 8 bits, well, I got 6 zeros and then 1, 1. And the question, how do I get directly to -3 from there? If I'm going to multiply this by -1, what really goes on inside the machine? So first, we'll take the 1's complement, ignore that spelling error, and then we're just going to add 1 to it. So the 1's complement means I just flip all of these bits. So the 0 becomes a 1, so I'll get 1, 1, 1, 1, 1, 1, 0, 0. So 6 1's and 2 zeros. And then I'm going to add 1 to it. That's going to give me 1, 1, 1, 1, 1, 1, 0, 1. And that's going to be the representation for -3. And you can, in fact, if you just look at the last 3 bits, if you do this with just 3 bits, ignore the first 1, 1, 1, 1, 1, 5 ones, we get 1, 0, 1. Or go ahead and do the math. Treat this as an exercise at home. So you'll take, this is going to be 1 plus 0 plus 4 plus 8 plus 16 plus 32 plus 64. Take away 128, and you'll find that you'll get -3. If we look briefly at the allowed range of numbers for signed versus unsigned representation, and I'm going to be using 2's complement representation from here on out because that's what's used in the machines in the lab and most certainly any computer you have at home. All right, so the number range. In the 3-bit example here, I was looking at numbers that go from -4 as the lowest up to +3. And in general, for n bits, a 32-bit machine will have 32 bits. What we'll see is we go from -2, and this is going to be raised to the n-1 power if I'm putting this into a formula. So here, 3 bits, 3 minus 1 is 2, 2 raised to the 2 is 4, so it's -4. And this is going to go all the way up to 2 raised to the n-1 minus 1 power. N-1 power, take away 1. So again, this is going to be 2 raised to the 2 power 4, take away 1 is 3. And that's what we saw here when we write them all out. And then for unsigned numbers, C lets us choose whether we're using signed representation or unsigned. What we see is we go from 0 up to +7. That was my very first example. And the formula for this is just going to be 0 up to 2 to the n-1. So 2 raised to the 3rd power would be 8, take away 1, gives me 7. So we can see we get to much higher positive numbers using unsigned numbers compared to when we use signed numbers, 3 versus 7. So if you're using a variable to represent like the counter in a loop that's iterating through an array where we only have positive integers that should be allowable, it can be really a good choice to use an unsigned number if we need a larger number for a bigger loop. Or if you're representing like the result of a mathematical formula that can only be positive, like factorial or the Fibonacci sequence, something like that, it can be better to choose an unsigned number for those sorts of number representations. Next, I'd just like to take a look at some of the bit patterns as we represent signed numbers and unsigned numbers, because both of these systems will be used on modern computers. So if we take a look at 3-bit representation of 1 as a signed number, we're going to get 001. But then if we take a look at the same representation for as an unsigned number, we still get 001. So both of these representations for a positive number have the same bit pattern in signed and unsigned. And then let's do another example. What about -1? So the -1 in 2's complement is going to be 111 for the bit pattern, but that same bit pattern, 111, is going to give us an unsigned value of 7. Let me just pull up that table from like the first slide. So there we go, 111 is going to give us 7. So if we're converting between a signed number and an unsigned number, and I'll talk a little bit more about this coming up soon, it can actually change the number when we change that representation. All right, I just want to do a little bit more with this using some larger numbers and converting to hexadecimal, because that's how things are going to be printed out when we actually start doing this in C, when we jump over to the code. So if we want to take a look at like a 1-byte integer, so this is the next step in difficulty, and this is just represented by char. If we wanted to do that, yeah, in fact, on older computers that didn't have very much memory, if programmers wanted to do math and they knew that they didn't need very big numbers, they would use char instead of int, just to save some space. It works the same as far as doing math. Just need to cast it back to whatever type you want to print out by using like the %d to print it as decimal. So anyway, with 8 bits or 1 byte, we see that we're going to get a number range of 2 to the 7th, the n-1, that's negative, all the way up to 2 to the 7th minus 1, or 128 up to 127. For an unsigned version of that, it's just going to be 0 to 2 to the 8th minus 1, or 0 to 255. Now the interesting part comes in when we start to try and represent negative numbers in signed numbers and unsigned. So for example, if I take -1 in 8 bits, the signed version of this of -1 is now going to be a signed int, which we've been using all along. We've just been calling them int. So we'd say like int num equals -1. And in the computer, this is going to be represented as all ones, 1111111, or in hexadecimal, FF. And then when we take the unsigned version of that to create an unsigned int, the type is just unsigned. This is I forget, I think I called it like a decorator or something when I was talking about short and long versions of int at the very beginning of the semester when we were talking about primitives. In fact, this int is optional. I can just call this unsigned if I want, and that's going to give me an unsigned representation. And so the bit pattern where I've got 8 ones is FF in hexadecimal. This is going to represent the number 255, the maximum possible number if it's unsigned. And we'll see that in just a minute when we start printing some of these things out in C. All right, guys, I changed my mind. I just looked at how much the time I'd already recorded has gone by and decided I'm going to wrap this up here and break and then prepare the... So if you think about Mondays and Tuesdays lectures, there's really 3 pieces to them. So I'm going to break that into 3 parts, and I'm going to do the second piece probably late tonight and then the third part tomorrow morning. So there'll be 3 pieces that represent the 2 75-minute blocks for these 2 lectures, but in 3 parts. So the next thing we'll do is we'll jump over the code and do some examples, but I'm going to put that in the next video. All right, I'm going to get this edited, rendered, and put up on YouTube, and then make that worksheet. So, all right, I'll see you guys soon.